So now that we've established that the Clapeyron equation can be used to look at slopes of lines on a phase diagram, we're going to take it one step further and we're actually going to develop not just a relationship between how P changes and T changes, but a direct relationship between P and T. If I look at the Clapeyron equation, it's a differential equation. Sure, it tells me how the slope behaves, but I can solve this differential equation for how P and T relate to each other. So we're going to do this for these three lines on the phase diagram. Actually, we're going to do two together and then you're going to do one for homework. So I'm going to start with this solid to liquid line. And we know some properties of this solid to liquid line. Depending on the densities, it might have a slight turn this way or a slight turn this way. But pretty much it looks a lot like a vertical line for many P's and T's. We're going to be able to analyze that again in the context of actually solving this differential equation, right? So if I was going to solve this first order differential equation, what we would do, like we've been doing all semester, is we would take the dt to the opposite side. So dp looks like delta H fusion, delta V fusion, dt over t, and all I did was rearrange this to group the t stuff together. Oh yeah, I'm talking about the solid to liquid transition, so I'm giving specific labels to my delta H and my delta V. These were labeled as transition before, but because I'm specifically talking about solid to liquid, we know we're talking about that melting point line where we have to deal with delta H fusion and delta V for fusion, right? Here's a differential equation that we can solve through integration. Let's say I'm looking at P1 and P2 on this axis, like a P1 here and a P2 there. And I'm going to integrate this guy, and I want to see what happens between a T1 and a T2 on this axis, right? And we kind of see what happens with this line, T1 and T2, and we made these arguments before, they kind of look like they're next to each other. They kind of look like there isn't much change at all. And we're going to be analyzing that in the context of this equation. To solve this, what we're going to do is we're going to make an approximation. And what we're going to say is these are terms that could possibly have temperature dependence and actually probably truly do. But for the sake of approximation, let's just say that they are temperature independent and constants relative to this integral. And let's pull them out front. So then what we'll have is an integral of dt over t, which by now you know and you can do, and integrate to a natural log. So what this is going to look like on the right-hand side is a delta H fusion that I pulled out, a delta V fusion that I also pulled out assuming temperature independence, and then a natural log of T2 over T1. On the left-hand side, I'm just going to get a delta P, okay? So I'm going to write that in there. All right. So this isn't clear, super duper helpful, because if I look at just sort of this little analysis here, well, T2 kind of looks like T1. And so what I have here is like the natural log of 1 by approximation for this term. And if I have the natural log of 1, the natural log term looks like 0. So it looks like I have like a 0 delta P. And so it's not like it's completely useless, but I really have to dissect this natural log if I want to talk about appreciable delta P's. The way that I like to analyze this equation is I like to take it and I actually like to make it about the temperatures. I actually like to kind of think about, okay, well, what would it take to see a different temperature, a different melting temperature for this line? So what we're going to do is we're going to take this equation that we have and we are going to solve it for T2, okay? Now to solve it for T2, I'm going to have to take these guys out in front of the natural log and bring them to the opposite side. So let's do that. So I'll have the natural log of T2 over T1 is equal to, right, my delta P, my delta V for fusion, over my delta H for fusion. And I just think this form of the equation is just easier to analyze things in terms of. Now, how do we get rid of natural logs? We use our e. So we raise both sides as a power of e. The e and the natural log over here, they cancel out. I'm going to have a T2 over T1, and I'm going to bring the T1 to the other side. I get T1, e to the delta P, delta V fusion, over delta H fusion. So all that right here is up in that exponential, okay? So now this, I think, is a little bit easier to analyze, and we can kind of see what happens, all right? So why is T2 close to T1? Well, if I look at this up here in the exponential, delta H fusion in general, for most phase diagrams, most little sort of delta P's, delta H fusion is going to be way bigger than delta P, delta V fusion. And that's just a general statement. So it kind of makes sense that I kind of get the same melting temperatures no matter what, because up in this exponential, if delta H fusion is so much bigger than these, it almost looks like I have an e to the 0, all right? And e to the 0 I know looks approximately like 1. So if this delta H fusion is just so much bigger than all that up there, it looks like e to the 0, which is approximated by 1, right? So it looks like I'm not getting a ton of movement in terms of what that melting temperature is if I change pressure on this axis. But I think what's possibly a more helpful analysis is what would it take, right, to actually get a T2 that's very different than T1. And if you look here in the context of what we have as experimental controls, right, if I get big delta P's, if I take that delta P and I make it bigger, then all of a sudden, right, this delta H fusion won't just divide everything and make it look like 0. If I take really big delta P's, right, and I analyze those, then this exponential term, right, this exponential term is going to be appreciable, and T2 will not just be equal to T1, okay? So looking at small delta P's, yeah, it kind of makes sense. You get different, you get T's that are kind of the same. Do you remember that water phase diagram we referenced from your book last set of videos? Remember what water's phase diagram did to actually see changes in this line? They took this P and they made this axis huge, okay? And they changed the units and everything on it just to see big changes in pressure. And what did you see? On that diagram where you saw huge changes in pressure, was this line perfectly vertical? No, because delta P is the true control, right? So what we see, the sort of take-home things for this analysis is we can start to talk about T2 and T1 and how they relate to each other. All right, we can talk about the slope and whether T2 is going to be bigger or greater than T1, looking at the values of delta V and delta H, but it also brings into question how delta P can control what you see in terms of T2 and T1. And for small delta P's, because of this delta H, for small delta P's, yep, these guys are going to be close. But to actually see changes in melting points, to see changes in freezing points, right? I have to take that P and I have to make that delta P bigger so that that exponential term starts to matter, okay? So we're going to apply similar thoughts, it won't be exactly the same, to other parts of this diagram. And I referenced it earlier. What we're going to look at next is the liquid to gas transition. And we're going to see that we generate a very sort of familiar equation to us. And this analysis that we're going to enact together for the liquid to gas transition, you're going to do it for homework for the solid to gas transition, and actually it's pretty much the same. It's very similar, okay? So we're looking at this line together today, the liquid to gas line. We already just analyzed this line here, all right? We see that there are changes in T as P changes, so it's a little bit more interesting of a situation. And then you guys for homework are going to use the same thought process and the same analysis for that sublimation line. So we're looking at that vaporization line right there. So we're going to start with the Clapeyron equation. dP dt looks like delta H now vap over T delta V vap. All right, T delta V vap. All right. Just for the sake of bringing it to things that we're familiar with later on, what I'm going to do is I'm going to make these molar, and we'll see why in a bit, right? So I'm going to make the top and bottom molar, which is fine. The units cancel out. Think about multiplying by n over n and then grouping things up appropriately, all right? I'm going to try to solve this in much the same way that we solved for the other line. So I'm going to bring the dt to this side. Delta H vap over delta V vap, dt over t. But then we have to pause and we actually have to think about the physical process that's occurring. What we're discussing here is a liquid going to a gas. So let's focus in on this delta V. right? Remember what delta V is going to be for this vaporization. It looks like V for your gas minus V for your liquid. And when you look at molar volumes, right, gases have enormous molar volumes relative to liquids. Even if you think about a gas and how it expands to fit the container that it's in, gas is just spread out crazy. They have a huge molar volume. So to a very good approximation based off that molar volume being so much bigger than the liquid molar volume, delta VVAP really looks like, well, just the molar volume for the gas, because there's going to be a negligible subtraction of the molar volume of the liquid. All right, so V of the gas, what happens if we have an ideal gas? So the first approximation is to kind of see delta V is really just looking like V for the gas. But then we also know that V, right, looks like RT over P for an ideal gas, right? RT over P. And so if that's the case, then what I can do is I can take this idea and this idea, and if we do some linking here, I have a delta V here. I make some arguments that delta V is really V for gas. And then I also know that if I have an ideal gas, V for the gas looks like RT over P. So I'm going to make this substitution right here. All right. So if we do that, I'm just going to give myself some more room here. Right? If we make that substitution, then on the left-hand side, we're going to have a dP. My delta H VAP hasn't changed. All right. My delta V becomes RT over P, and I still have this dt over T term left. Well, now I see if I want to solve this differential equation correctly, what I've done with the assumption that delta V is really just V for the gas, and V is an ideal gas, so I can replace it with P over RT, I have to bring this P to this side. All right, I absolutely have to bring this P to this side. I also see that I don't have just one T in the denominator now. I see that I'll have a T times a T in the denominator. So if we keep going with this thought process, on the left-hand side, we're going to have dP over P. On the right-hand side, we're going to have delta H VAP over RT squared dt. Right? This can be integrated. And on the left-hand side, when we integrate between a P2 and a P1, we're going to get the natural log of P2 and P1. Over on this side, we're integrating between a T2 and a T1. And remember, we're still talking about that liquid to gas line. We're going to have a delta H VAP over R, right? dt over T squared. This is a very important equation. Let's simplify it down. This is like a good equation to know. All right, delta H we know does depend on temperature. So it's a starting point where if I have a functional form of delta H, I can throw it in there. But let's go ahead and let's make it simple. And let's pretend that delta H VAP is not a function of temperature. And let's pull these guys out. All right. What we're going to get through this integration then is once we do the integral, delta H VAP over R is on the outside. And on the inside, we have T to the minus 2 dt between T1 and T2. All right. So think about doing an antiderivative here. What we're going to get is delta H VAP over R unchanged, right? And here we're going to get a minus 1 over T evaluated between T1 and T2. What I'm going to do with this is I'm going to bring the negative out front, all right? And I'm going to do that analysis, keeping track of correct mathematics in terms of how we do those analyses. We substitute in the variables and we subtract. And what you'll see is we're left with something that's very familiar. The natural log of P2 over P1 is equal to minus delta H VAP over R 1 over T2 minus 1 over T1. Now, this is an equation from general chemistry that we throw at you, right? Without ceremony, without actually saying where it comes from. But now you see where it comes from and now you can derive it. And this equation from general chemistry is the Clausius-Clapeyron equation. And it actually comes from solving, right? Solving the Clapeyron equation, right? The differential equation, and getting a relationship between P and T instead of dP and dt, okay? Now, remember the important approximation that we made for the Clapeyron equation. It's not going to be valid all the time. The Clausius-Clapeyron equation is valid when that has no temperature dependence, when your delta HVAP is not temperature dependent. And we know that the temperature dependence of H, it could manifest under certain situations, okay? But for those nice situations, right, where we do have a delta HVAP that can be approximated as a constant value, then here we have a situation where we have this equation that really just relates different P's to different T's, okay? So this is an equation we should know how to use from general chemistry. I'm going to give you some practice problems just to kind of get used to using it again. But now we see where it's coming from. You're going to be able to redo this derivation in the context of gases, right, coming from solids. So think about what you just saw. Think about what we wrote down. When I give you a homework problem that deals with solids to gases, can you justify the same approximations? What changes about this equation, right? What stays the same? Think about those ideas as you're doing that homework problem. And as always, send me any questions that you have.